Welcome back, everybody. Chapter 5, Active Feedback Control Systems, as they are applicable to spacecraft attitude control problem. So what would we need active control if we've seen in the previous chapter that then passive stabilization techniques work? Well, yes, those passive techniques work, but as I've mentioned in the past, are not very accurate. You end up with inaccuracy in terms of alignment or pointing, precision and accuracy of about 10, 15 degrees might be sufficient for your given mission you have for the spacecraft, but in general, we'd like to have a much tighter and better control of our spacecraft as a whole, okay? And for that reason, we need to use actuators that will be applying torques to our spacecraft to maintain its attitude exactly where we want it. Or in other words, we're going to use our actuators to fight the perturbing torques that are being applied to our spacecraft and pushing it and moving it around. All right. So the first thing I want to do in chapter 5 is just go over some preliminaries, kind of as a refresher. So we're going to talk about transfer functions and how to combine transfer functions together and how this is related to the spacecraft attitude control problem. So let's do that. Chapter 5. Active feedback spacecraft control. All right, a couple of things I want to set the stage for here. And the first thing is the use of the dynamical model that we're going to base the design of our controllers upon. All right, so we know that the dynamical equations of motion for spacecraft rotational motion can be done through Euler's equations of motion. We saw that way back in chapter 1. The problem with that is that those equations are coupled together, as we saw, and are nonlinear because of the gyroscopic term. That's your omega q times j omega. So for design purposes, those equations are a little bit complex and beyond the scope of this course. Because if you want to use a nonlinear dynamical model to design the controller, then you need nonlinear design control techniques. And again, this is beyond the scope of this course. We will be talking about graduate level, like master's and PhD graduate work for nonlinear control. But because we want to design linear controllers, we need to have a linear dynamical model for the plant or for the system which we're trying to control. Okay? And in our case, that system is going to be the spacecraft rotational equations of motion. So we need to take some assumption here. So we will assume that the angular velocity components in the body fixed reference frame are small. Okay? And that will allow us to simplify the gyroscopic term in the equations of motion to 0. The gyroscopic term being your omega q j omega actually contains multiplication of angular velocities, as we've seen in the past. So two components that are being small multiplied together will be approximated to be equal to 0, and therefore would allow us to rewrite our equations of motion for principal axis body fixed reference frame to simply be Jx roll rate, Jy pitch rate, Jz roll acceleration, pitch acceleration, and yaw acceleration, not rate, equal to the external torque being applied about the x-axis, about the y-axis, and about the z-axis. So by making that assumption, we've been able to decouple our equations of motion completely. Okay? So that is a net advantage, and they share the exact same form, such that ultimately what we'll end up doing is to design a controller for one axis and just copy and paste the same controller to manage the other two axes. Okay? Now, the torque terms we have on the right-hand side of those equations will, in practice, be a combination of two things. The net perturbing torque, tau p, along the x-axis, net perturbing torque along the y-axis of your body fixed reference frame, and the net perturbing torque about the z-axis of your body fixed reference frame, plus the controller's output. Okay, so the controllers are there to apply mathematical equations to calculate what would be the best torque to be applied to the spacecraft to ensure that it follows as closely as possible a desired attitude. Now, that desired attitude could be a time-varying attitude in terms of the trajectory. It could just be a set point or whatever. It's up to you. But all this to say that we do have second terms here that are being added to the undesirable perturbation terms. And those additional terms here will be the control outputs, tau c x, tau c y, and tau c z. Okay? So those signals correspond to the outputs of your controller. So if you were to draw a block scheme diagram, CTL, the controller, we calculate the torque, components, and body fix. That torque will be fed to the dynamics equations of motion here to calculate the yaw or roll acceleration, pitch acceleration, and yaw acceleration based on those equations of motion. But also the other input that comes in here is from the environment, and that would be the net perturbing torque, including gravity gradient, aerodynamic torque, solar radiation pressure torque, magnetic torque, and so on and so on, okay? So net perturbation being added to control torque to then change the acceleration in terms of Euler angles in our equations of motion. Okay? And because, again, they share the exact same form, all three axes being decoupled, we're going to generically denote our dynamical equations that we're going to be playing with throughout this chapter as being a generic angle denoted theta. Okay, and that theta does not longer correspond to pitch. That could be any of the three Euler angles. And then just J, because J could be replaced by Jx, Jy, Jz. This is now a generic principal moment of inertia equal to perturbing torque, tau p, plus control torque, tau c. Okay? And we're going to call this the system which we're trying to control, or in control system theory, this is widely referred to as the plant. So our plant is a single axis in terms of rotational motion of a spacecraft whenever the angular velocity vector is small in terms of its x, y, z components, such that we've been able to neglect the gyroscopic term in the equations of motion. Okay? So we're going to say that based on that, the plant output, or the output of the system being controlled, will be a rotational angle, theta, generically speaking. But in terms of feedback control theory, the output of the plant is also widely denoted by simply y. Okay? So y will be our generic plant output, but just keep in mind that within our application here, which is spacecraft rotational motion control, the plant output y corresponds to either roll, pitch, or yaw, denoted generically by a theta angle. Okay? The plant input in our case will be the net torque being imparted to the spacecraft, so perturbing torque about one axis plus control torque about the other axis. But in terms of feedback control system theory, the plant input is generically denoted by U, okay? So sometimes I will refer to U, or sometimes I'm going to refer to the net torque being comprised of perturbation and control signals as the plant input, but just keep in mind that they refer to the same thing, okay? The Y in U notation is used all across the board in feedback control system theory. Whenever here for rotational motion, we use theta specifically and tau as the plant input. Okay, so that kind of sets the stage for 5.1, which hopefully will be some sort of review of transfer functions and other properties of linear systems. The transfer function representation. So the beauty of neglecting the angular velocity components, or saying that they are small enough to be able to neglect the gyroscopic term in the equations of motion, is that now that we have three decoupled equations with one input and one output, and that those equations are linear, and we can easily model that using the transfer function representation. Okay? So we're going to say that transfer function, or transfer TF for short, is actually a very useful tool to model any systems with a single input and a single output. Those kind of systems are widely referred to as CISO system. Single input, single output. Okay? So based on what we have, which is our J theta double dot equal to control torque plus perturbing torque. If you want to obtain the transfer function of a time domain equation, all you have to do is to take the Laplace transform, obviously, and you would end up with J S squared theta in terms of the Laplace domain equal to control torque in the Laplace plus perturbing torque also in the Laplace domain, like that. Now here, keep in mind that I didn't include the initial conditions because for transfer functions, it is not necessary to do so. We used that in previous chapters as a way to see the effects of our initial conditions on the motion, but typically, or generically speaking, you can consider that initial conditions are kind of external to the system. Yet the outputs of the system will be ultimately function of the input provided to the system as well as the initial conditions. But here, transfer function is only a modeling tool that is representing the relationship between the input and the output without the effects of the initial conditions. All right? Such that we're going to say that the transfer function of our plant will be equal to the output of the plant, Y, in the S domain, over its input. This is the generic way of denoting any transfer functions. But here, in our specific case of spacecraft rotational motion, we're going to say that our output will be the rotation angle, like that, over the input, and the input is going to be those two torque being added together. So the control torque, or the action of the controller, plus the effect, undesirable or desirable effects of the environment into which our spacecraft is evolving. Tau C in the S domain plus tau P in the S such that by solving that equation for theta over this, it's easy to see that all you're going to get is your 1 over j s squared as a transfer function specifically applicable to one axis of a spacecraft undergoing a rotational motion. And for that reason, this particular dynamic model is known as a double integrator model. Because in the S domain, an integrator is 1 over s, and now you have 1 over s squared, thereby referring to it as a double integrator model. Okay. So all this to say that you can model the spacecraft in terms of a single axis as being GP, like that. That calculates outputs here, given its input, whereas the output will be equivalent to an angle in terms of roll, pitch, or yaw. It doesn't matter because they were all sharing the same dynamical equations in the time domain. And the input here will be the net torque, being comprised of two components, control torque and perturbing torque, like that. And this is your spacecraft in terms of rotational dynamics about a single axis, say BZ, like that. And you would have to copy and paste this box 2 other times to capture the rotational motion about the other 2 axes, because the spacecraft is not only rotating about one axis, generically speaking, but about 3 axes simultaneously. Yet, through this mathematical modeling, we have considered that all 3 axes were perfectly decoupled from one another. Okay, now that is the plant input, but let's assume that this plant input is actually coming from the output of another system ahead of the plant. That's convenient, because that is exactly the situation we're going to end up with, because whatever will feed the plant with something will happen to be another transfer function corresponding to the controller. So let's now suppose that U of S, the plant input, is coming from another system, i.e. the output of that system, right? So the output of the other transfer function or system corresponds now to the input of the plant. So let's say we have our plant transfer function, GP, with its input signal. And let's assume that this input signal is coming from another transfer function denoted by H. And H could be whatever. All right? But H takes as input W, like this, such that you can write, and here you have the output of your plant like this. Which means that H of S, in terms of transfer function representation, will be obtained, as usual, with the output over its input, W. But we know from before that the output of our plant, Y of S, was obtained from the transfer function that multiplies the input, U of S. Remember, because G of P had been said to be y of s over u of s. So solving that for y of s gives you that relationship. But we know then from before here that u of s could be obtained from h of s, the other transfer function or system ahead of the plant, times the input of that other system, such that ultimately the output of everything, y of s, will be equal to this transfer function that then multiplies the other transfer function times its input. Or you could say that the global output of those two corresponds to the multiplication of those two transfer functions times the global input W. That's what this equation means. Turns out that this is known as a series connection of systems, or alternatively you could say of transfer functions. Yes. And graphically you could just represent that as one input, a big transfer function that will be h of s multiplied with your plant transfer function, and that you get the global output y of s at the other end. Okay, so this is series connection. The other possibility that can take place is known as a parallel connection. As the name implies, that will be whenever you have two systems or two transfer functions organized in a parallel configuration. Okay, let's say you have G of P and H, but this time organized like that, where you have a branching point that splits the same signal into the same thing but twice. If you denote this as U of S, and then the output of the individual systems or transfer functions will be added together to form the global output being denoted by Y of S. And let's denote the output of this one only by Y1, and the output of that one as Y2, plus, plus. Okay? So if you look at trying to determine how could you replace this configuration with something more compact and more elegant, or in other words, how could you combine those two transfer functions into a single one that will map the global output to the global input, while all you have to do is to track the signals, okay? So we have Y of S being equal to Y1 of S plus Y2 of S. Okay. What is Y1 of S equal to? Well, that would be GP times U. So let's substitute this first with the transfer function GP times U. Plus, similarly, how is Y2 obtained from U of S? Well, simply through H of S times U of S. And you can obviously factor the U of S signal out of these two terms and write GP of S plus H of S, like this, will give you Y of S. And if you're looking to find the net transfer function of those two elements and the summing element as well, and that would just be the output, global output, y of s, over the global input, u of s, will simply be equal to gp plus h of s. And that would be the combined transfer function. So, in other words, you could replace all this mass by simply one box. That would be the summation of the individual systems here, or individual transfer functions. That would do the mapping directly between y of s and u of s. And again, this is known as a parallel connection. Okay. The third type of connection I'd like to go over with you today is known as the feedback connection. And the reason for that is because, well, surprise, surprise, in feedback control systems, we will often encounter a feedback type of connection. And that would be super useful to know how to simplify a block scheme diagram into only one or two transfer functions at the end of the day to do the mapping between the plant output, which would be, in our case, the current rotational angle of the spacecraft about a single axis, and the global input of everything, which would be the user's provided desired angle. Okay, so the user would say, I want the spacecraft to point in that direction, yet it is pointing over here. So those two things represent the input and the output, respectively, of the global system. And the controller's job will be to actuate in a specific manner the spacecraft such that the current angle comes in and tracks or arrive at its destination and stays there. Okay? So feedback connection. We'll look at this here I'm using GP for the plant, but that could be applicable to any kind of transfer functions. It doesn't need to be a plant dynamical model. That could be something else, all right? And this is being fed back into another transfer function that we had denoted by h of s. This signal is being added like that, and that is denoted as u of s, the global input. We have the global output here with a branch connection, and here we'll denote the output of h of s in that example with a of s, and this signal being u of s minus a of s will be denoted as b. Okay? So the question is the same. How could you find a transfer function that relates directly the global output, y of s, to the global input whenever the systems or the individual transfer functions are organized in a parallel fashion, or, sorry, not parallel, but feedback fashion? Well, you could say that a of s, the output of this, is obtained through the transfer function h of s that multiplies y of s. Okay, I'm just reading the diagram and turning this diagram into equations. And this is a skill that you need to master to handle most situations we will encounter in Chapter 5. Okay? All right. But what do I know about y of s? Well, I know that y of s is actually equal to GP that multiplies B. Okay. But what do I know about B? I know that this signal B is actually obtained as u of s minus a of s. So all I have to do is to plug everything backwards and say that my y of s is therefore gp of s, that multiplies u of s minus a of s, like that. And that therefore my a of s here can be re-expressed in terms of gp, h of s, u of s, and a of s, and then solve that to get the output over the input. I'm going to say, therefore, a of s, the original equation, is going to be equal to h of s times gp of s times y, but y is this with the gp, but times u of s minus a in the s domain. Okay? A of s, I'm going to pull all my a of s on the same side to write that it is going to be equal to 1 plus h times gp, close the bracket, and all this equal to u of s, and multiplies h with gp of s. Over here. Okay? Where did the y of s go? Yeah, I went too far in the process. But that could be something that could be useful to get the relationship between that and that, if that's what you want. That's not what I wanted. Did I do a mistake? Maybe. Let's do that again. Let's do that again. Without the notes. Okay. First, I'm going to drop the function of s because everything is function of s, and that will just speed things up. So y of s is equal to gp times b. Or in other words, gp times u minus a. Okay? Or y equal gp times u. A is equal to h times y. Okay, that works out. So that will allow me to get the relationship between y and u. So all I have to do is put my y's on the same side. 1 plus gph equal gp u. What I did. Yeah. Okay. Or if I want to solve for the net transfer function of everything, it means I'm looking for output y over input u, and therefore we write this as being gp over 1 plus gp times h. And this is actually the transfer function I was looking for, or in other words, how to replace this big feedback loop with a single transfer function that does the mapping between u and y. Well, this is going to be the transfer function in the direct loop, okay, like that. That's your GP over 1 plus GP times the 1 included in the feedback loop, like that. GP over 1 plus GPH. And that'll be used quite often because, again, feedback connections are employed frequently in feedback control system design. All right, so that kind of summarizes what I wanted to say about transfer functions in terms of preliminaries. So next, I want to talk a little bit about the feedback control duality problem. And I'm not sure if that was actually covered in your feedback control system design course, but I feel that this is something which is quite important to realize to better understand the limitation of feedback control systems. Okay. And that would be in 5.2. Feedback control system problem. All right. So let's go back to what we know for spacecraft rotational motion. We have our transfer function of the plant or the spacecraft itself. Is going to be equal to the output, which is the angle of rotation, over tau c plus tau p, right? The torque terms being applied to the spacecraft itself. Or generically speaking, as I've mentioned before, this can also be referred to as y of s over u of s. So this is the plant model. Okay, which is equal in our case to 1 over js squared, but for this discussion, that is not necessary to know, okay? Now, what is the objective here? Well, it turns out the objective of any control law is to ensure that the output tracks as closely as possible the desired signal as provided by the user. So we want to make the output of the plant to follow a desired trajectory or simply get to a desired angle or value. Yeah, then that's all. So we want to make theta follow a desired trajectory specified in terms of desired angle as function of time, or simply get to a desired angle value, theta d, which won't be a function of time, okay? So generically speaking, we want to say that we want to make the output of the plant to follow what's known as a reference signal. That could be theta d function of time or just theta d. And that reference signal is going to be denoted as R of S. Okay? Now the controller's job, given that this is the objective we're shooting for, controller's job is to ensure that RS minus, generally speaking, minus y of s. So the desired angle provided by the user, i.e. u, minus the current angle of the spacecraft rotational motion along one axis. Well, that has to be as close to 0 as possible, okay? Or in other words, we're going to say that the control error, which is equal by definition to reference minus current output and denoted by E of S, has to reach 0. That would be in a perfect world. If that's the controller's job, then that kind of implies that the controller needs to know at all time the value of this. So for that reason, we have the controller's transfer function denoted by GC of S, which is going to be equal to the input, well, the output over input, where the input is going to be the error signal. And the output of your controller will become the input of the plant, which is going to be U. Okay? If you were to neglect perturbations, obviously. Okay, the controller does not generate perturbations. Perturbations are just part of the environment. But the controller will generate a signal that is going to be fed actively to the plant, or specifically to the actuators, to make sure that they respond in real time, to ultimately make sure that the tracking error between what you want and what you have reaches 0. Okay? But to know this implies that we know the current output of the system, or the current angle of our spacecraft, about one axis. So how can we do that? Or how can we ensure that the onboard controller has that information available to itself, such that it is then able to figure out what it needs to perform the control action? Well, in practice, this is obtained through sensors. Those are devices that are installed on the spacecraft or any dynamical system that are there to measure the current output of the system. If you think about a speed control, cruise control on your vehicle, which is a speed controller essentially, well, the onboard controller needs to know the speed at which you're traveling at, and then compare that to the command. So command is 110 kilometers an hour, and the sensors are measuring a current speed of 100 kilometers an hour, and therefore there is an error of 10 kilometers an hour, and thereby, based on that, the onboard controller will do some math, and will say, okay, well, we need to accelerate by this amount. Okay? So sensors are a fundamental part of any feedback control systems. The problem with sensors is that they won't provide you with the real value of the current output of the system, because sensors are mechanical / electronic devices, and therefore they're not 100% accurate. Or we could say that they are noisy. Okay? Sensors, by their fundamental nature, will introduce noise in the system. Okay? So if the real speed of your car is 100 kilometers an hour, function of time, that would be speed v, the sensors on board the car might read something roughly equal to 100 kilometers an hour, but with some variations. Okay? Because of the noise. And therefore the controller, which only has access to the noisy signal, will think at some point that you're going actually a little bit slower than 100 kilometers an hour, but in reality the car was at 100 kilometers. So the controller signal, which would be the desired acceleration to be imparted on the vehicle to make sure that you reach the set command of 110, will be slightly inaccurate. Okay? So here, because the controller thinks you are slower, it's going to provide a larger acceleration that was actually needed, and then the actual speed will maybe go above a little bit or overshoot the command, things like that. So noise is an inherent part of any control system, and because control systems rely on sensors. Okay, in other words, the sensors are providing you with a signal equal to the actual real output of the plant, but corrupted by noise, like that. So this is noise added to the realistic output of the system. So again, all this to say that the controllers will be provided with an error signal that will be the user command minus the realistic output, but corrupted through sensor noise, like this. So if you were to put everything we've learned thus far in a block scheme diagram, while you have your plant, or in terms of spacecraft rotational motion, that would be the dynamical model of a single axis spin, okay? Because you know that everything can be decoupled about the 3 unit directions of your body fixed reference frame in terms of angles. So that could be the model of roll, and then another for pitch, and another for yaw. But again, we're doing one axis at a time, so I'm not going to copy everything 3 times, okay? So this is the output of your plant, which is your JP transfer function from before. This actual signal is fed back, and through sensor block will then add an adverse effect, and that adverse effect is the noise, W, okay? This is being added to Y, and this is the signal with which you're going to compare the reference value with. Plus minus the reference signal. I need more space. Plant Y back here, and that is the error signal. This error signal is being fed to your controller, GC of S, which will calculate the control torque. Say how C, but generically speaking, that would be your U signal. Okay. But U doesn't go directly to the plant because of perturbations as well. Okay. So there is another summing block here where perturbations are coming from. That would be your tau P signal coming in. Okay? Plus, and those two together are being fed to the plant. Okay. So if you look at that from the big picture, you can say that this entire system has 3 external inputs, right? Because if you were to enclose everything in a box, like that, you clearly see that we have one input over here, the reference signal. We have another one over here, perturbations coming in, and the noise coming in from the sensors. So 3 inputs. Perturbations, reference signal, and sensor noise. And we have only one input, one output. So one output, which is going to be our Y of S, as usual. So the question becomes, how those 3 inputs affect the output of the system, or what would be the relative contribution of, say, perturbations on the output with respect to these other 2? Would this overpower sensor noise, or would this be overpowering perturbation torques in terms of contribution to output? Well, we don't know. Turns out that because we are dealing with linear systems, we could use the superposition or superimposition. Superposition. Is that even a word? To superpose or to add together the individual contributions from those three outputs one at a time, and then sum the entire thing together, okay? And that's exactly what we're going to do by first examining the effect of the reference signal on the output of the system, Y of S. Okay? If you want to do this, it means that you need to turn off the other two inputs. So to analyze the effect of that, we pretend that there's no noise and that there's no perturbations. And then to analyze the effect of perturbations, we'll have to turn off the reference signal and the noise. And finally, to analyze the effect of the noise, we'll have to turn off those two other inputs. This is the superposition or superimposition. I don't know, just pick the right word here. Principle that works because we are dealing with linear systems. Okay. So that's what we want to do. It means that we will set the noise equal to perturbations equal to 0. And in that case, we will denote our output as being output due to the reference signal R only. Okay? Y of R in S domain. All right, so let's do that. So now we don't have this coming in, and we don't have this coming in as well, which simplifies the block scheme diagram quite a bit. Okay, so what we want to establish here is the relationship between Y and R only. And in that case, we're going to refer to Y as Y of R. Okay, so let's begin with this. Y of R is actually equal to, again, I'm just reading the diagram here. GP that multiplies what's coming in at its inputs. And because there's no perturbations, I can forget about this summing block. So GP times U. But I know that the U signal is the output of your controller. So GC times the input, which is E. YR. But I know that the error signal is the difference between the reference signal and in that case, Y of R without any noise. That would be R minus Y of R, like that. And it turns out I have all the signals I need, those two and that one, to establish the transfer function between this input and that output. So let's pull the YR on the other side and write YR multiplies 1 plus GP GC will be equal on this side to GP GC times R. And because I'm seeking the relationship between YR over the reference signal, that means that this is going to be equal to GP GC over 1 plus GP GC, like that. Okay? So let's keep that in our back pocket. That will become handy ultimately when we're done analyzing the individual effects of the individual inputs, because we're going to sum all these three transfer functions together to get the contributions of everything at the same time onto the output. Okay, so YR over R equal to GP GC over 1 plus GP GC. Good. So that is the effect of the reference signal on the output. Now let's do the same, but this time for perturbations. So this is coming in now, tau p plus plus, but there's no sensor noise and no reference signals. Okay, so I want the relationship between y, which will be now denoted yp, because that will be y based solely on the contribution of your perturbations. I'm going to say effect of perturbations on the output y. So in that case, I'm going to set my RS equal to my sensor noise equal to 0, and I'm going to denote my y to be yp of x. Okay, so what I'm going to do here is I'm going to start here at the output and just translate this block scheme diagram in terms of equations just by multiplying transfer functions with inputs to obtain their outputs, as I've done so far, okay? Again, this skill to transfer from block scheme diagram to equations is a fundamental skill that you need to master to do well in this course. So, yp is equal to this transfer function, gp, times whatever comes in, and that happens to be u of s plus tau p. U plus perturbations. Now u of s is actually gc times e. Yp equal gp, and this u is gc times the error and plus perturbations. Okay, I can go further and then close the loop here by writing that gp then multiplies gc, and the error is simply minus yp, right? The minus sign is still there. We didn't take that out. All we took out was the reference coming in, with the plus here. I'm going to say that the error is simply minus yp plus tau p. Or alternatively, by flipping the yp term on the left-hand side, I'm going to say yp multiplies 1 plus gp gc will be equal on this side to gp tau p. And because I was seeking the relationship between this output and that input specifically, I'm going to write yp over tau p equal to gp 1 plus gp gc. Very similar to the last one, yet slightly different. So let's report it here. We want to make use of it later on. So gp over 1 plus gp gc. Good. So you see, all I'm doing here is I'm reading the signals flowing through the diagram and turning that into ultimately a transfer function that relates the output of interest to the input of interest. So far we've established the effects of reference signal and perturbations on the output. So let's now analyze the effects of the sensor noise which is W, onto the output of the plant. In that case, we need to shut down those two other signals that were coming in previously. So no more perturbations and no more reference signal. So effect of sensor noise on Y. Okay, so again, we are setting here perturbations equal reference equal to 0. And because this is the effect of sensor noise onto our output, I'm going to denote my output as being YW. So Y of S now rewritten as YW of S. Okay, so same procedure as before. I personally like to start at the output of the global system, but you could start at anywhere in the flow of the signals and you would end up with the same answer, okay? But to me, this is more intuitive to always start with the output here. So YW is equal to GP times U. Going a bit faster because I assume that you've got a hang of it by now. U is equal to GC times error. GP, GC, what is the error equal to? The error is going to be equal to minus of W plus YW. Minus of W plus YW, like that. Okay. And do I have everything I need? I have my YW as my output. I have my input here. I'm good to go. So now I just need to, factor out my YW everywhere. W plus GC YW minus, sorry. Okay. I can flip this on the other side and write YW multiplies 1 minus plus GP GC will be equal to minus GP GC W. Or alternatively get my transfer function between this input and that output. So it's always output over input, obviously. Would be equal to minus GP GC over 1 plus GP GC. There we go. So YW over W equals minus GP GC over 1 plus GP GC. Excellent. And note that I could have gone even faster by remembering the series connection and just combining those two from the get-go as being GC times GP and forget about this intermediate signal, okay? But I did it step by step so that you learn how to translate any block scheme diagram, even those that you cannot use directly, the series or parallel or feedback connections we've seen previously. It's just a matter of reading the signals and how they flow through the individual transfer functions. Okay. So we're going to say that the combined response of the system, and we're allowed to do that because this is ultimately a big linear system. Okay, there's no nonlinearities involved. We're going to say that Y will be equal to the combination of YR plus YP plus YW. Okay, YR will be equal to R times GP GC over 1 plus GP GC. plus what is yp equal to? Flip this here, such that yp will be equal to tau c to tau p. I think it was tau p, right? Perturbating torque. Yeah, that's tau p gp over 1 plus gp gc. Okay, and lastly for yw is going to be minus w that multiplies gp gc over 1 plus gp gc. So ideally, in the ideal world, what would we like to have? Would we rather have the output of the system follow the reference, or be equal to the reference, or equal to tau p, or equal to w? Well, those two things are nasty effects. We don't want our output to be equal to the perturbating torque. That would just be silly. Or our output to follow the noise of the sensor. That'd be, just not right. So what you want is to have the output of the plant to follow the reference signal as provided by the user. Okay? And let's say we want this to be equal to that. This is our objective. And this is referred to as perfect tracking control. Okay? If you are ever able to achieve that exactly, it means the controller is perfect and is able to cancel the effects of noise and perturbation altogether. But that's not that trivial. So how could you get that from that expression? Well, an obvious choice would be to set your controller to infinity. Okay? Doing so will get you infinity over infinity, which is 1. Okay? That's great. That would be p over infinity. So that'd be good, because that would mean that this is 0, and therefore you've been able to cancel the effects of the perturbation. But here you end up with infinity over infinity, or 1. Can't happen, sorry. So in other words, there is no way that you can design a controller that will simultaneously cancel the effects of the perturbations as well as canceling the effects of the sensor noise. You can do one, but you can't do the other one. Here, through the choice of controller transfer function to be infinity, we've been able to cancel the effect of the perturbations affecting the plant, yet the noise is still going to be present in the overall output when all three inputs are considered. Okay? By another choice of GC, we could have canceled the effects of the noise, but then perturbations would have remained in the net response of the system. And this is known as the duality of control system design. Okay? There are ways to get around it with more advanced control techniques, but if you stay in the linear realm, you'll always have to deal with that kind of problem here. Okay? This is something fundamental about feedback control system that I wanted you to be aware of, because I don't want you to think that linear control is perfect and will be able to do always what you want. Okay? When you dive into nonlinear or adaptive or robust control techniques, those are much more powerful. Yet we need to start somewhere, and that somewhere will be linear control system design, which we're going to dive into next time. So everything we did today was kind of preliminaries to hit the ground running in the next lecture, where we're going to talk about different types of control systems and whatnot. All right. Hope you're still following along. Hope you're having fun and that you're doing great in the course. Till then, stay safe, and I'll see you next time.